Lab 3 is about RNN sequence models. And so what we've done so far is we formulated the problem, looked at the code base, trained an MLP on just MNIST. That was lab 1. Lab 2, we introduced extended MNIST with characters, and we trained CNNs on it. And then we also generated lines of handwritten characters. And this week, we're going to train a CNN, at first just a CNN, and then also LSTM to recognize those lines that we generated. So, in the breakdown of our text recognizer Pro, we're working on the line text recognizer. Let's go ahead and switch over to the README. This is what I'll be working on VS Code. You guys can do this in Colab when you do it, or set up your computer to do it. So always remember to git pull. That's how you get the new lab. And then you go into lab 3, which I've done now. So there's a number of new files in this lab. We have all of our data sets are the same as from lab 2, including the EMNIST lines. In lit models, which are kind of the wrappers around our actual models, there's a new one. There's a CTC lit model, and a metrics.py and a util.py. And then in our models, there's 3 new ones, and that's LineCNNSimple, and then LineCNN, and then LineCNNLSTM. And we're actually going to go through them in sequence. So LineCNNSimple is the first one I want to go through. And the first thing I want to do is actually look at the notebook from last week. So you can actually open notebooks in VS Code, which is really pretty useful. I'm not going to run it. I will just remind you of a couple of things. The first is that our class mapping, right, the mapping of integer labels that our model is going to output to actual tokens that we can print, includes these special tokens, B, S, E, and P. And so we'll talk about them this week. P is the one for padding. So we just pad all the strings we generate with that special token up until max length. And this is what our data looks like if we generate our data without any overlap. So that means each character, remember EMNIST is 28 by 28 pixels. If we just kind of take a 28 by 28 character, plop it down, then do another one next to it, another one next to that, but there's no overlap, this is what it would look like. It doesn't quite look like handwriting, but it's getting close. And this is the first thing that we will try to do. So flipping back to README, we're going to use this model that we introduced called LineCNNSimple. And let's go ahead and look at the code. So it's in text recognizer models, LineCNNSimple. And this is actually not accurate. We'll just delete that for now. So what it does is it actually instantiates a CNN. So the same one that we used last week to recognize characters. That's what we're going to instantiate in this model, right? And then the forward method of this model takes an input that's batch size by number of channels, by height, by width. That's the input image. And the height and the widths are now different because if you look at what the images actually look like, width is like 400 something, height is still just 28. And what we'll output is a batch by number of classes. This is number of channels, so I should call it something different, but it's actually just one for us because we have a grayscale image. So it's batch by number of channels by sequence length. And the first thing we're going to do is actually compute what S should be, because we're able to do that because of two arguments or hyperparameters that this model takes, which are window width and window stride. And that's the width of the window that we're going to slide over the image and the stride of that slide, basically. And it makes sense when you look at this, right? So if window width was 28 and stride was 28, then basically it would be looking like this, right? If window width was 28 but stride was 14, then this is what it would look like. And then window width can also be 14 itself with stride 14 and so on, or it can be 14 with stride 7 or 14 with stride 10. So basically we can control these parameters independently. And then what we'll actually do in this model is first compute the number of windows total, which we can do with some ConvNet math, just like last week's. Basically, it's the width of the image minus the width of the window divided by the stride of the window plus 1. That's going to be how many windows we're going to look at. And then for each window, we'll actually just send it through the CNN that we instantiated. So the CNN takes an image and outputs a activations over classes, right? Over all the characters that are possible. And what we're going to do is we're just going to sample windows and run each one through the CNN. And that will fill out activations. So we can train this with this command. So run experiment, let's run for 10 epochs on a GPU, with 1 GPU, with 4 data loading workers for speed, emnist lines class, and we're going to do minimum overlap 0 and maximum overlap 0. So that's going to get us this like very spaced out characters. And the model class LineCNNSimple, and we're going to set window width to 28 and window stride to 28. So we're basically going to sample character by character. So we load the data, then we load our model, which is 1.7 million parameters. And it's really just it's the same exact CNN as in last week. We don't have any extra weights. We just apply it over windows in the line. And right away we're getting our validation accuracy up to like 89%. So it's working just about as well as it did, you know, when looking at one character at a time. So what loss function are we using here? So with this command, we didn't specify any special loss function. So it's using the default loss function, which is cross entropy. So it's using the cross entropy loss. And if we look at the PyTorch docs for cross entropy loss, it takes an input and the target. So the input is N is the batch size, C is the num classes, right? And that's going to be our input. So it's like each slice, for each element in the batch, we're going to output, like we could output the activations where C-sized activations vector. Or we could output this in case of k-dimensional loss, right? And that's exactly what we have. So for target, that's the ground truth. Our target used to be just a single integer, right? It used to be some integer between 0 and c minus 1. But now it's actually a vector. And it's the vector that's basically for each character in it, right? So it'd be T, H, E, padding, padding, padding. And that's simply called k-dimensional loss. And it works quite well. We trained it. It gets 90% accuracy. So that's as simple as this can be, right? What we can do now, though, is let's change the window stride such that we're sampling windows that are overlapping and not something that's right next to each other, but something that's overlapping. So let's go here, and let's just set it to maybe window stride, let's say 20. So now we're doing something like window size 28, but window stride is 20. So we're going to overlap a little bit on each window, just like this. Trying to we got an error here, and it's expected target size 44, 128, that's the batch size, 44, that's the sequence length, but we got torch size 128 by 32. And that's coming from the loss function, which we can see here. And that's actually expected because we're returning, remember, we're returning like the sequence length that we're returning depends on the window width and the stride. And it just worked out that for 28 and 20, it works out to 44. But our ground truth is still 32 because at most there's 32 characters in one of our lines. That's okay though, because we have this limit output length, which is one of the hyperparameters, or I guess arguments to the model. And so if we set it to that, we're going to limit it to what the data set expects. So we can go ahead and just add that limit output length. So now it's going to work again, but it's not going to work as well as it previously did. And the reason for that is because we actually know how this data was generated. Like, there is no overlap in the characters, but now there is overlap in our model. And so the model is not exactly aligned to the characters. So the accuracy is about 52, whereas before it was already, you know, up in the 80s, even after the first epoch. So this isn't going to really converge to something that's as high as before. I maxed out at like 60% accuracy. Okay, so what we can do then is we can actually make the data overlap by a quarter, right? So that's roughly going to match this 28 and 20 stride. So if I cancel this and run something where I change this from 0 to 25, so that's going to correspond to each character being basically overlapping by a quarter. And that's not actually going to, that's not actually going to make the characters overlap because there's still white space around the characters. So let's just make sure that it trains a little bit better. So now we're getting accuracy up into the 70s. And this will actually end up with accuracy into the 80s, but I'm gonna stop the training process right now. Because what we really want is variable length overlap, right? We want something that looks like real handwriting, which first of all, each character has a different width, right? Like a T and a W are just different widths. Whereas in this data set, they're not. Everything's always the same width. But also, different people have different handwriting. Sometimes you space your letters out, and some people really write them close together. So we can approximate that a little bit with a variable length overlap. So if I say max length, 34 characters, max overlap 0.33, so a third, then our min overlap is 0, our max overlap is 0.33, and we'll actually just sample the overlap for each letter. And that results in lines that look like this, which looks much more like real handwriting. And that's going to be a challenge for a model right now, because there's basically no setting of window width and window stride that's going to match all of these different, essentially synthetic handwritings. And so we're going to set min overlap 0, max overlap 0.33, and then window width 28 and 20, and just like see what happens. So first it's gonna, generate the data, load the model, and it's gonna start training. And we're not gonna let it train for full 10 epochs, but the best I was able to get is around 60%. And that's because the model is just unable to handle that variable overlap. Now, we know how to fix this, right? We can introduce the CTC loss and then basically oversample in our CNN. So set the stride to something that generates a lot of windows, and then just use the CTC loss to handle those repeating characters that we'll probably be outputting. We'll see that working in a second, but before I do that, I just want to introduce LineCNN versus LineCNNSimple, because LineCNNSimple is really quite inefficient, because if the windows overlap, it actually just recomputes a bunch of convolutions on that overlapping area, right? Because it takes this window, runs it through the CNN, and then it takes, let's say, this window, which is like largely overlapping with the previous window, but runs it through the same CNN, which will do a lot of repeated computation. And this can really add up over the, especially if you have a lot of convolutional layers. So what we can do is make a fully convolutional network, and that is LineCNN. So just like before, we have our conv block, conv1, conv2, conv3, except this time we're using convs for downsampling. So we used the max pool last week, but now we use a stride 2 conv instead. And then we're actually going to introduce a conv which acts much like a fully connected layer, because its size is going to be basically like as big as its input, right, vertically, and then a big window horizontally. And so we essentially have a convolutional layer that is acting like this. And you should take a look at this on your own time. But the forward method is just as before: conv1, conv2, conv3, conv4. We do a little bit of conv math to predict the sequence length, make sure that the sequence length is actually what we think it should be. And then once again, apply fully connected layers on top of that, just for good measure. And it basically works the same as LineCNNSimple. So I can just run the exact same experiment as before, except with LineCNN. Instead of LineCNNSimple, it'll run a tiny bit faster, and it's just a little bit nicer. So we'll continue with that. But the real magic is going to be in the CTC loss, okay? And the CTC loss will be implemented by a different lit model. So far we've been using this base lit model. So remember, the lit model is responsible for initializing the optimizer, initializing the loss function, any metrics you might care about like accuracy, and then defining what should happen in the training step, the validation step, and the test step. And what should happen is basically we apply our model to the input, and then we compute the loss against the expected output, and we also compute the accuracy. So that's the base lit model. The CTC lit model is slightly different. So it still has it still defines the optimizer. The loss function it's going to use is torch and then CTC loss, which you should read about. And then the metrics are going to be accuracy, but also this new one called character error rate. And it's something that we define ourselves, actually. And it's from this metrics file. And part of the homework is actually just to describe what this character error rate metric does. So in the training step, what CTC lit model does is apply the model to the input, You get logits from the model. For the CTC loss function, we actually need log probabilities. So we apply softmax or log softmax to the logits. The CTC loss expects, things in this order: sequence length, then batch length, then number of classes, whereas our model returns batch length by number of classes by sequence length. So we just permute the dimensions. And then it also expects a couple of things, namely input length and target lengths. I'm not going to talk too much about it. But basically, it takes the log probabilities, the ground truth, the input length, which we just set them to the sequence length, and then target length. These are actually like the ground truth target length, excluding padding. So we compute those. And then in the validation step, we also want to compute the character error rate. So additionally, we have this greedy decode function, which part of the homework is to describe what this function does. But in essence, the CTC loss does this collapsing of repeated characters and removing of the blank token. At inference time, we need to do that also. And so we need a special function to remove blank tokens and collapse characters. And that's what this greedy decode does. So you're going to have to look at this as part of the homework. For now, we're just going to use it. So what we're going to do is, so the best we got, once again, is 62%. So we can run the same exact experiment as before. I got 62% accuracy. And instead of limit output length, we're going to say loss equals CTC. And when we say loss equals CTC, it actually uses the CTC lit model. And you can see that in run experiment. So when loss is CTC, the lit model is actually the CTC lit model. A little bit of a hack here. So let's go ahead and run that. Okay, so it's training exactly as before. The loss is going down, which is nice to see. The speed is about the same as before. It's not any slower. The error rate is going down from 99% to 70%. The error rate is only computed for the validation, in the validation step, not the training step, because that greedy decode function that has to be run actually is kind of expensive. So we only do it in validation and test. But there you go. It's training quite well. The error rate is decreasing, and it's the exact same model as before. So the only thing that changed is the loss function, and it's working a lot better. And lastly, one thing we can do is add LSTM on top of that. The last thing we want to add on top of this is LSTM. And so we'll let this train. It's already down to 18% character error rate. So LineCNN takes an image, takes a batch of images, outputs batch by number of classes by sequence length. Let's look at LineCNNLSTM. So first of all, it initializes a LineCNN. So this same model, the one that takes an image, outputs sequences of class logits, we're going to initialize it inside of LineCNNLSTM. And then we're also going to initialize an LSTM. Okay. And then also a fully connected layer on top of that. And in the forward, the forward method of the LSTM, what we are going to do is take the input, run it through LineCNN, which gives us those activations, number of classes by sequence length. Permute it, as necessary for the LSTM to make use of it, which is basically just switching the batch and sequence dimensions. and then run the output of that through the LSTM. Okay, and the LSTM is actually bidirectional, which we initialized it as bidirectional. And so the next thing we do is we just sum up both directions of the LSTM, because what it outputs is like sequence length by batch length by 2 times the hidden LSTM dimension, and we just kind of sum across that. Then we apply a fully connected layer just as another step, and then we get it back into the format that our LitModel expects, which is batch size by number of classes by sequence length. So we got 16% character error rate with our LineCNN model and CTC loss. And so now we can just say LineCNNLSTM right here. Run it again. The inputs that it expects are the same. The outputs that it provides are the same. So nothing really has to change. The only thing that changed internally is now there's an LSTM processing the output of that CNN and kind of hopefully using the contextual information that the hidden state can encode to make an even better prediction. It's more parameters. So our old model was, let's see, 1.7 million parameters. The LSTM one is 2.3 million because we have some additional parameters in the LSTM layer. So it's training. We can take a look at our GPU load. Looks like it's nice and fully loaded, 96% utilization. And the loss is going down. The character error rate is going down. And if we let it train, you know, it might end up in a slightly better place than without the LSTM, or maybe not. And it'll also depend on your window width, your window stride, and stuff like that. So part of the homework is just experimenting with stuff, like try, you know, different window width, window stride, maybe LSTM dim, number of layers. Better yet, you know, edit LineCNN or the LineCNNLSTM files and get crazy, you know, add attention to the LSTM if you want, and then describe what you did, paste code if that's appropriate, if you edited code, and kind of what you learn. It doesn't have to be too intense. And then also, we want you to look at what the CTC lit model is actually kind of doing. And so part of the homework is to describe this character error rate metric and also the greedy decode function. So that is it for lab number 3.